is this one here, right? And watch what happens. A lot of times what we tell our students to do is just to see what happens. If you plug in 15 pi over 2 right there, it's going to be 0. But if you plug in 15 pi over 2 right there and for theta, the tangent of 7 theta, I typed it in here into my calculator. Watch, let me stop the share. So I typed in the tangent of 7 times 15 pi over 2. It's kind of blurry, but there it is. And if I hit equals, look at my calculator, it gets unhappy. It says error. So that means that you cannot actually do that. You cannot plug in the 15 pi over 2 into the tangent of 7 theta component. So plugging this in is a fail. Here, since we're talking about the squeeze theorem, you have to find a function to compare this with. So usually when you compare it, so let me go like this here, let me go like this here. So usually what happens is, usually you keep one of the components of the original expression, usually. And in this case, I want to keep the cosine theta. I want to keep that one there. I want to keep cosine theta. I want to keep cosine theta. So, but now what I have to do is I'm going to have to find something that I know that this is bounded by. So the cosine of tangent of 7 theta, what is this bounded by? Well, recall that if you have cosine of whatever, that can be whatever. I don't care what that is. As long as it's defined, I don't care what this is, whether it's positive or negative or a small number or a big number, I don't care. Because regardless of how big or small this is, cosine of that is going to compress it. It's going to sandwich it down to either 1 or -1 or something in between. So for that reason, this yellow bubble is less than or equal to +1. And that same yellow box is greater than or equal to -1. And so that's how I've decided to make my boundaries. I am going to bound this function above by this and below by that. So let me take my eraser tool and take off that line there. And so now what you have to do is you have to show that, let me grab the pencil. You have to show that this limit is equal to this limit. And if these limits are equal, then the middle one is going to have the same limit value. So let's actually find that. So let me erase this here. And let's find the limit of the one above, and let's find the limit of the one below. So let me grab the red tool here. So I want to find the limit. Let's go in red. I want to find the limit as theta approaches 15 pi over 2 of essentially cosine of theta. And then I want to find the limit as theta approaches 15 pi over 2 of negative cosine of theta. So that's when you take out your calculator or the unit circle, whatever. You can do this on the unit circle, on the calculator. Make sure your calculator is in radians. You can show that if you plug in 15 pi over 2 in for theta, you're just going to get back 0. And for this one as well, you're going to get back 0. And because our function is bounded above and below by functions whose limit is the same thing, then for the middle piece here, which is the original problem, the limit for theta as it approaches this of that guy is also going to be 0. So what you always do is find an upper and a lower boundary, but not just like anything. Find something that's above and below, but it has to be something that works to your advantage. You want to find an upper function that if you take the limit at whatever you're approaching, that you can actually get that answer quickly, in this case 0. And the same thing for the lower function. Find an upper and lower function that are convenient, that the limit of them can be found quickly. And then by the squeeze theorem, the limit of the original problem, which is bounded above and below, it has no choice but to conform itself to whatever these limit values are. So in this case, it was 0. So if you have more questions, send them my way. I'd like to do a problem where the limit wasn't 0 because we could learn more from them. So try more questions and please send them my way.